Hey guys, how you doing? This is a video lecture on section 3.2. In section 3.2, we're examining relationships between bivariate data. So we have an x, an explanatory variable, and somehow it influences in some way your response variable, which is on the y-axis. And now we're going to talk specifically about the line of best fit. And the line of best fit that we're going to use in AP Statistics is called the LSRL, or the least squares regression line. Okay, the least squares regression line is a model. So it best fits the data, but it doesn't exactly fit the data. Remember, it's a model. Just like the normal model, there's going to be some error. And we talked about this in section 3.1's lecture. And now we're going to define that error, and we're going to show you how to calculate the error. Okay. So here we are in section 3.2. And here's our learning objectives. You're going to interpret the regression line, calculate the equation of the least squares regression line, calculate residuals, and construct and interpret the residual plot, determine how well a line fits the observed data, and interpret computer regression output. So here is kind of the example that kind of threads through the entire chapter. And in this example, what we have is for 8 weeks, we had 16 healthy young adults that I think they were overfed, and we wanted to measure, well, what was their fat gain after 8 weeks, okay? And we regressed the fat gain against their NEA, or their non-exercise activity. So non-exercise activity is defined as activity that burns off calories, but it's not classified as like formal exercise, right? So it's like fidgeting and things like that, okay? So here is the scatter plot of the actual data. So each one of these blue dots is an actual observation, which happened. So there should be 16 of those dots. And each one of these is an actual observation, okay? This red line is the predicted, that is the LSRL, okay? It's the regression line that predicts how much fat gain, okay, will be added after a certain amount of NEA. Okay, so for example, how you read this red line is if you input a value of 800 for NEA, 800 calories, what does our model predict? What does our red line predict would be the fat gain after 8 weeks? Well, you just simply find the 800, where does it intersect, and then go over here, and you would estimate what this value would be, okay? So regression lines, the regression model, regression lines are used in the real world primarily for prediction, So we have a model, this line fits this blue data, this red line fits this blue data. It's actually the best fit for the blue data. And anywhere within, the scope of this model, we could predict how much fat gain there would be for any given level of non-exercise activity. We want to be careful, though, not to do what's called extrapolate. We don't want to, this model falls apart. It is only good from about, this part from about, negative 100 to about maybe a little bit more than 700. Okay? We don't want to use this model to predict values that are way outside of this, like 1,000 or 1,500 or 15,000, right? So if somebody's NEA increased by, 2,000, could we predict what their fat gain would be? No, because that's called extrapolation, because that is too far outside of the scope or the range of our model. Our model is only good from about, minus 100 to about, 700, maybe a little more than 700. Okay, so now how do we interpret the regression line? Well, the regression line, again, it's a model, and it shows you a predicted y. It shows you a predicted value for y based on an actual x that you could plug in. Okay, so the regression line has the equation of y hat, not y, but y hat. Y is different. Y would be one of the actual observations. So all these blue dots are the actual 16 people, the 16 healthy young adults, and it's their actual value of non-exercise activity and their fat gain after this 8-week study. Okay, so like this dot has an X and a Y, has an actual X value and a Y value. Okay, this red line, okay, is where your Y hat would be. Okay, Y hat, all your Y hats are on this red line. Okay, Y hat is the predicted fat gain, not the actual fat gain, but the predicted fat gain. So Y is the actual fat gain, and Y hat is the predicted fat gain. Okay? A plus BX. So A we recognize as the y-intercept, and B we recognize as the slope. So it's very important that you learn and memorize this statement on how to interpret the slope and how to interpret the y-intercept. So how we interpret the slope, and you're going to do this in context, okay? But the slope tells us how much the predicted y, not the actual y, but the slope tells us how much the predicted y increases when x increases by 1. So if you increase x by 1, so plug in 1 there, well, b times 1 gives you b, so y hat increases by b units. Okay? So the slope tells us how much the predicted value of y will increase given an increase in x by 1 unit. And you're going to use the context. Okay, and we'll do that in just a moment. A is the y-intercept, and of course if x equals 0, this whole side of the equation, or this entire thing just zeroes out. This term zeroes out, and then you just get y hat equals a. So A tells you what is the predicted value of y, not the actual value of y, but A tells you what is the predicted value of y when x is 0. And sometimes that's very useful information, and sometimes that's not useful information. It all depends on the context of whatever problem you're dealing with. Okay, so you have to think very carefully when you're interpreting the A, when you're interpreting the y-intercept. You also have to comment on whether it's reasonable in the context of the problem. Okay, sometimes it's unreasonable. Okay, so let's go back to the LSRL for regressing fat gain to non-exercise activity. Here is the actual equation. Notice that they use the actual contextualized words for your y and for your x. Okay, so how do you read this? You read this as predicted fat gain, not fat gain, but predicted fat gain is equal to 3.505 minus 0.003444 times NEA change. Notice again they use the actual contextualized explanatory variable there. Okay, so now let's identify and interpret the slope in context. The slope, first way to identify it, the slope is equal to what? Well, it's negative. Make sure you report the negative. The slope is equal to negative 0.00344. How do we interpret that? That tells us that for an increase in NEA change of 1 calorie, notice that I'm using the actual context, I'm using the units of measurement. So as NEA increases by 1 calorie, the predicted fat gain, not the fat gain, but the predicted fat gain increases by negative 0.003444 kilograms. Okay. Another way to say that, probably that makes more sense, is that as the non-exercise activity increases by 1 calorie, our model predicts that the fat gain will go down.